All right, let's see what is in store for us in the homework in this section where we're just getting comfortable with the idea of eigenvectors and eigenvalues. So let's start off with numbers 2 and 6 from the homework. I think that probably 6 is easier to start with than 2. So let's just start with 6. It says, hey, is this thing an eigenvector of that? And easy enough to check. We just need to do the multiplication and see if we get a multiple of 1, negative 2, 2. So you can do this on a matrix calculator, or you can do it by hand, whichever way seems quicker to you. I'm going to try to do it by hand and see what happens here. Hopefully my brain's in good shape. So let's see, that'd be 3 minus 12 is negative 9, plus 14 is 5. Next row, 3 minus 4 is negative 1, plus 14 is 13. This is already not looking good for being a multiple of what went in. I'll check the last one just to make sure. It'd be 5 minus 12 is negative 7, plus 8 is 1. That is definitely not a multiple of what went in. So this is the answer there would be no. That's not an eigenvector of that particular matrix. Okay, so on to number 2, which might take a little more work, because here they're just saying, is this particular number an eigenvalue? So keep in mind the idea, again, for eigenvalues, is we're looking for a minus lambda I times some vector to produce the 0. So let's do 1 minus negative 3, so 1 plus negative 1 plus 3 is 2, 4, 0, 6, and then 9 minus negative 3 would be 12, 0. Keep in mind, if the only solution we find here is the 0 vector, then that doesn't count for V, and that eigenvalue did not produce an eigenvector, so it's not an eigenvalue. On the other hand, if there's some other vector that works this way besides the 0 vector, then we do have an eigenvector that goes with this eigenvalue. I can already see when I row reduce here that I'm going to only have one pivot, so there is going to be a free variable, so there is going to be a solution. So I can already say yes, it's an eigenvalue. But let me go ahead and actually, so let's just say yes. But let's go ahead and actually find the eigenvector that goes with it. So added value here. This is more than the homework asked to do, but when you row reduce here, you do negative 3 of the first row to the second row. So that becomes 2, 4, 0, 0, 0, 0. And you can say something like, well, actually, let's divide the first row by 2 also. 1, 2, 0, 0, 0, 0. There, fully reduced. So this first equation says x1 is negative 2, x2, and x2 is the free variable. So the vector that solves will be any multiple of negative 2, 1. So just plain old negative 2, 1 would certainly work. I'll choose x2 to be 1 here. So we'd say lambda equals negative 3 has an eigenvector of negative 2, 1. And if we really want to double check that, which we do, of course, because it's me, we just want to say, hey, does it actually work? Does negative 1, 4, 6, 9 times negative 2, 1 actually produce negative 3 times negative 2, 1? So it should produce 6, negative 3. Let's find out. So negative 2 times negative 1 is positive 2. 4 times 1 is 4, so that makes 6. This becomes negative 12 plus 9, negative 3, which is indeed negative 3 times negative 2, 1. Ta-da! We've proved at extensive length that yes, lambda equals negative 3 is an eigenvalue of this particular matrix. And furthermore, we found out the eigenvector that goes with it and checked the whole thing. So we went beyond what they asked. Okay, let's look at a couple more questions from a little bit later on. And here they're really just asking you to do what we did for number 2. So they're saying, say, find a basis for the eigenspace corresponding to the listed eigenvalue. So this time they're saying, yeah, it definitely is, and let's figure out what it is. So same idea, we are trying to solve a minus lambda I times v equals 0. I'm going to jump straight to the row reduced augmented matrix, or straight to the augmented matrix, then we'll row reduce. So negative 4 minus negative 5, so negative 4 plus 5 would be 1, 2, and then augmented with 0, 3, 1 minus negative 5, 1 plus 5 is 6, 0, and there I can see I'm going to have a free variable when I reduce. So 1, 2, 0, 0, 0, 0 is the reduced version of a minus lambda I. And the solution to that I can see is x1 equals negative 2, x2. This seems kind of familiar, huh? And x2 equals x2. And factoring that out, we get negative 2, 1. So there's the basis for the eigenspace. All right, it is any multiple of negative 2, 1. So it is the span of negative 2, 1. So it is a vector space, particularly it's an eigenspace. And the basis vector is negative 2, 1. So it should be that if I multiplied negative 2, 1 times a, I would get, what, 10, negative 5, and you can double check that to make sure. I won't do it this time. And same thing on number 14. I just wanted to do 1 3 by 3, just so that's not a shock to the system when we get there. Same idea though, it's going to subtract 3 from the diagonal entries. So that would be 1, 0, negative 1, 0, 3, and this is 0, but it's still a diagonal entry, so 0 minus negative 3 would be negative 3, 3, 0, 2, negative 2, 2, 0. And now we get to row reduce. You can certainly do this by hand, or you can grab a matrix calculator if that's more efficient for you. Maybe I'll do this one with a calculator, so hold on a second. Okay, so we want to reduce that, and we get that. So I'm going to see if I can write down my solution vector here right away. This would be x1 equals x3, and x2 equals 2x3, and x3 is free. So x1 equals x3, x2 equals 2, x3, and x3 equals x3. Factor the x3 out, and you get 1, 2, 1 as the basis for the eigenspace that goes with the eigenvalue of 3. And again, it should be that if I multiply this by 1, 2, 1, that I would produce 3 times that. So I'd get 3, 6, 3. And keep in mind, any multiple of 1, 2, 1 also works here. So if I had done 2, 4, 2, I should have gotten 3 times that out, so 6, 12, 6. But anyway, you can just double check it with 1, 2, 1. 1 times 4, 0, so that's 3. 3 is 6, and 2 minus 4 is negative 2, plus 5 is 3. Yep, it works. Okay. So I think you should be ready to plunge into the homework. Have fun with eigenvalues, eigenvectors. Try to work the word eigenspace into casual conversation today. And we'll see you in section 5.2.